Hello everyone, I'm Divya, your math facilitator. I'm here to help you out in the very last days of your board exam. So here I have planned all the 14 chapters for you, and now I'm going to start with the first two chapters, real numbers and sets. So I'm going to complete all the concept and I'm going to tell you the previous year questions and the most important and expected questions for this year. So I hope this video will be very helpful for you and I'm very sure about it, and I want you all to share this particular video with all your friends so that everyone is well versed with these two chapters. So let's begin the session. But before I start the session, I just want you all to have your pen and book with you, because those things which you have learned months ago, I'm going to revise it within hours. Okay, so it's going to be super important for you. Complete revision is going to happen, and after the class, once again, you will have to revise whatever we have learned in the class. That can be done only when you make notes of this particular class. So please write the important concept and important questions which I'm giving you, so that it will be helpful for you for your revision. So on this note, I hope you are all ready with your books and pen. So let's begin. First, let us discuss the concepts related to this particular chapter. Okay, so yes, the very first concept which we have in this chapter is Euclid's division lemma. Is it so difficult? No, not at all. What is Euclid's division lemma? See, we have been doing division since our childhood, isn't it? And it is something we have been learning and we know it very well. So Euclid's division lemma is something related to that. Okay, so suppose if I want to divide 7 by 2, how do I divide 7 by 2? 2 3 is a 6 and 1 is a remainder. So now this 7, which is a dividend, you will get it. Okay, this 7 is a dividend. Okay, this 7 you can get it as if you multiply the quotient and the divisor. Okay, divisor into quotient. Divisor into quotient is 2 3 is a 6. Plus the remainder if I add. Plus remainder. So this is giving me the dividend. Is this clear? So this rule you have already used in your primary classes to check if your division is correct or wrong. The same thing we are again using it here. Okay, so what are we doing? Dividend is equal to divisor into quotient plus the remainder. This is nothing but Euclid's division lemma. Okay, you might be wondering, but here something else is written. Then what it is? It is the same. So suppose if A is a dividend, if I divide it by a number B, okay, I get some quotient and I will have some remainder. Then in the same process, I can write A is equal to divisor into quotient plus the remainder. The same thing we are writing it as A equal to BQ plus R. Got it? This is nothing but Euclid's division lemma. And and the most important thing here is, sometimes when we divide, our remainder is either 0. Yes or no? Suppose if I divide 6 by 2, my remainder will be 0. Or here, if I'm dividing 7 by 2, my remainder is 1. So I'm getting a remainder 0, or I will get a remainder which is less than the divisor. What is the divisor here in this case? 2. So my remainder is either 0 or it is less than 2. Okay, the same rule applies here. The remainder which you're getting here, okay, it is either 0 or it is less than your divisor. Here divisor is B. So I can say my remainder lies between 0 and B. Okay, it can be 0 or it can be less than B. So something between 0 and B you can have, or equal to 0 as well. This is nothing but Euclid's division lemma. Now proceeding to the next concept, fundamental theorem of arithmetic. Very simple. It tells you whenever you have a composite number, okay, that composite number can be prime factorized. Okay, you can express in the form of a prime product of prime numbers. And the most important thing is that prime factorization is unique and the order of the prime numbers can be different. Very simple thing. Suppose if I take the number 12. 12, is it prime or composite? Is 12 prime or composite? It is definitely a composite number. So this composite number, if I ask you to prime factorize, so some of you might take 3 as the first number. So 3 fours are 12, 2 is a 2 ones are. So one prime factorization is 3 into 2 into 2. Another prime factorization, suppose if I take 2 to 6 are 12, then if I would like to take 3, I can. So 3 2s are 6 and 2 ones are. So 12 I can write it as 2 into 3 into 2. Or there is some other person who comes and says, I would like to take 2 first, so 2 6 are 12. Again, I would like to take 2 only, 2 3s are, and then 3. So 12 can be written as 2 into 2 into 3. Just observe all the 3 prime factorizations. All these are the prime factorizations of the same number 12. Okay, but if you just observe all the 3 prime factorizations, you will find that all the 3 prime factorizations are same. In all the 3 prime factorizations, you see there are 2 2's. Yes or no? You have 2 2's and 1 3. Clear? But if you observe the order is different. Okay, so prime factors are same, but the order can be different. This is nothing but fundamental theorem of arithmetic. So a composite number, which is 12, it can be expressed as product of primes. Can you find? 12 is expressed as product of prime numbers. But how is this product? There are 2 points. First point, the product is unique. Okay, this prime factorization which you're getting is unique. Unique means it is special. Suppose if I take number 12, so prime factorization of 12 is special. Okay, so it is, see, you have 2 2's and 1 3. Any case, however you want to do, you always have 2 2's and 1 3. Okay, this is the meaning of it. But the order can be different. Okay, so you have 3 2 2, 2 3 2, 2 2 3. So the order is different. But ultimately, when you count, there are 2 2's and 1 3. So that is called unique. Clear? So when I take a composite number, that particular composite number can be expressed as product of prime numbers. And this prime numbers, prime factorization is unique, which means however you do, you will get the same prime numbers. Okay? And then the order can be different. Clear? This is nothing but fundamental theorem of arithmetic. Next, you have 3 more theorems related to each other. So I'll just summarize it for you here. See, theorem number 1.3, the first theorem tells you if x is a rational number, what is x? X is a rational number. Okay, x is a rational number. Rational number is in the form of p by q. Right. Then x can be expressed in the form of p by q. Yes, we have already expressed x is a rational number, so it can be written in the form of p by q. No worries in that. Then the prime factorization of q. Then this q which you are finding in the denominator, this q prime factorization is 2 power n. It is 2 power n, 5 power n. And what type of rational number it is? It is a decimal form which terminates. Okay, x is a rational number. Let me write it very clearly. X is a rational number, and how is the decimal expansion of this rational number? It is terminating decimal expansion. Okay, it is terminating decimal expansion. Then the denominator q can be written as 2 power n, 5 power n. That means 2 power something, 5 power something. Both 2 and 5 you can express. Theorem 1.4 tells you if x equal to p by q is a rational number, and if q is of the form 2 power and 5 power, then it will have a decimal expansion which terminates. So here they are telling you if this is a rational number, if x is a rational number, and here if q is 2 power and 5 power n, then it will give you a terminating decimal expansion. Okay, these two are reverse of each other. Now 1.5 tells you that if x is equal to p by q is a rational number and the prime factorization of q is not of the form 2 power and 5 power n, then it is non-terminating repeating. Here you find it. So x equal to p by q. Okay. And q is not of the form 2 power n 5 power n. Then if it is of the form 2 power n 5 power n, then you will say it is terminating. If it is not of the form 2 power n 5 power n, then it is called non-terminating, non-repeating. This one slide will help you in all the three theorems. Okay. If x is a rational number, then if it has a terminating decimal expansion, then q is of the form 2 power n 5. If x is a rational number and if q is of the form 2 power n 5 power n, then it is terminating decimal expansion. If x is a rational number and q is not of the form 2 power n 5 power n, then it is non-terminating, non-repeating decimal expansion. Clear? So now let's proceed to the next one. See here, p is a prime number, p divides a square. Then p also divides a. For example, let me take a as 4 and p as 2. Okay? P divides a square. A square is 16. So they're telling you that p divides a square. That means this p, which is 2, is dividing 16. Yes, it will divide. Any doubt in this? It's dividing. Then what is the conclusion? Then this p will also divide a. Yes, it will also divide a. No confusion in this. Right? So if this is possible, then this is also possible. Okay? If p divides a square, then p divides a. Clear? So proceeding to the next one, we have formulas of logarithms. So just have a look of that. So first of all, logarithmic form is an inverse function of exponential form. What does it mean? Suppose if I have a power x equal to n. If I have a power x equal to n, then if I apply logarithm, then I can write x is equal to, this power is equal to log n, applying log this side, log n. This a, which is the base of the exponent, will become base of the logarithm. Clear? So whenever when you write the exponent, this is the power and this is the base, isn't it? So this base of the exponent will also become base of the power. Clear now? Base of the logarithm, sorry. So clear? So now just have a look. So let us see the different laws of logarithm. Like we have this is similar to a power m into a power n is equal to a power m plus n. Yes, multiplication becomes addition of the powers. Right? The same thing here. Log xy to the base a is equal to log x to the base a plus log y to the base a. So here it is product, and when you split, it will become addition. Okay. Log x power m equal to, this m just jumps in front of the logarithm and says I'm m log x. Okay. And log a to the base a is 1. Log x by y, this division will become subtraction. Okay. Just as we have this exponent formula, same like that. Okay. Then a power log n to the base a. Here I told you this is the base of the exponent and this is the base of the logarithm. When you have these two same, directly this n will be the answer. And log 1 is always 0. No doubt in that. Log 1 is always 0. So I'll just wait for 30 seconds. Just try to remember all these formulas. So I hope you have revised it. So let's proceed to the next topic. Just nothing but the problem. So till here we have completed all the concepts of the real numbers chapter, and I hope each and every concept is very clear to you. So now let's begin with the problems. So problems also, I'm only taking the most important problems which you can expect in the board exams. Yes, the very first one, use Euclid's algorithm to find the HCF of 900 and 270. So one I will do, the other I will give you as homework. Okay. Out of the two numbers, choose the bigger number as the dividend and smaller number as the divisor. We know A is divided by B, so you have a quotient and remainder. So how do you write? A is equal to BQ plus R, isn't it? A is equal to BQ plus R. So now this 900, let me divide with 270. Okay, and let us see how many times can we cancel it. So 270, how many times can we take? For this, you will just have to take 27 table. Okay, so suppose if I take 27 table, 27 twos are 54. Okay, if I take 27 fours are, it will be more than, it will be 108, I guess. So 27 three times we shall take. Okay, so 27 three times will be 81. Okay, so 273 times will be 810 then. Okay, so 273 times is 810. So you have how much? 90 as the reminder. Okay, so this statement, this first division, let us write it like this. How do we write? First dividend is equal to divisor into quotient plus the remainder. Now I hope you remember this method, continued division. Now this remainder 90 will become the divisor. This 270, the previous divisor, will become the dividend now. And we know 9 3 is a 27. So 93 is a 270. So this part of division, how can we write? Dividend is equal to divisor into quotient plus remainder. Whenever the remainder is 0, so who is the HCF here? 90 is the HCF. So whenever remainder is 0, you will take the divisor as the HCF. So therefore, HCF is clear. Anyone? Any doubt in this? Right. Look at the next question. So here you have any positive odd integer, you have to prove it is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Okay, so let us take any positive integer first. And we have to prove using Euclid's division algorithm. Okay, so let any positive integer, I'm taking it as A. Okay, so we know that if A is in a positive integer, now just compare. We have to prove it as 6q plus 1, 6q plus 2, 6q plus 3. If you compare, we have A is equal to BQ plus R. So in the place of B, what do you have? 6. So we are going to take B equal to 6. Then our remainder will be less than 6 and it will be 0 or equal to 0. Okay, it will be between 0 and 6 basically. So let us take case number 1, first case. So with this we have 6 cases actually. Okay, so let me just erase it. So first of all, substituting this value b equal to 6 in the Euclid's division algorithm, we have Euclid's division lemma says a equal to bq plus 6. But substituting b equal to 6, we have a is equal to 6q plus 6. Let this be equation 1. Okay, this notes will be shared in mathfacilitator.com website. Do visit and download this notes and learn. It is completely free. Okay, and if you have not yet liked the video, please do like the video right now. So now let us take case 1. Case 1 tells you remainder is 0. Okay, if r equal to 0. Here when I say r is between 1 and 6, we have some cases. What are they? R equal to 0, 1, 2, 3, 4 and 5 till 5. So first I'm taking r is 0. If r is 0, your first equation will be a is equal to 6q plus 0 or simply 6q. Or see here, we need, it is a positive odd integer. Okay, what is the meaning of odd number? Odd number is of the form 2n plus 1. Yes or no? Okay, if I get any number as multiple of 2, like 2n, this is called even number. Yes, so here this number I can write it as 2 into 3 cube. So 2 into something will become an even number. So this is not odd. What is this? Even number. This is not the case we want. Let us go to case 2. R equal to 1. So first equation will become A equal to 6 cube plus 1. So this is nothing but I can write this as 2 into 3 cube. 6 I can write 2 3s are plus 1. So 2 into 3 cube is even. Just now we have discussed. Plus 1 when I have even. To even number if I add 1 it becomes which number? Odd number. Okay. So let us go to next case. Case 3. When R equal to 2. So A will be equal to 6 cube plus 2. So just have a look. If I take 2 common, I will have 3 cube plus 1 here. So 2 into something, this will become simply even number. Okay. Let us take case 4 now. R equal to 3. So A will be 6 cube plus 3. Okay. Here, if I take 2 common, okay, so this will be even number here. And plus 3 is nothing but a odd number, or simply I can also take it as, see here, just to prove it as odd I'm telling you, if I take 2 common here, okay, here I have 3q plus out of this 3 can be written as 2 plus 1. So this 2 I can take it as common, plus 1 I will have. So some even number plus 1, this will become odd number. Did you understand here? First of all, 6 cube plus 3 is odd number. How is it odd? So to this even number, I am adding 3. Okay, if I add 2, then it will again become even number. For example, 4 is a even number. If I add 2 to this, it will become even. But if I add 3 to this, it will become odd. Understood? Right, so this is actually odd number. Now let us take case 5, r equal to 4. So first equation will be 6 cube plus 4. So if I take 2 common directly here, so 2 into something, this is actually even number. Let us take the next case. Case 6. Case 6 is A is equal to R is equal to 5. Isn't it? If I take R as 5, the last case, then the first equation will be A is equal to 6 cube plus 5. Again, same logic I will tell you. If 4 is a even number, if I add 1 to it, it will become odd. If I add 2 to it, it will become even again. If I add 3 to it, it will become odd. Just now I told you. If I add 4 to it, it will become even. If I add 5 to it, what will it become? Odd. So this is basically an odd number. Okay. So if you just look at the question, what do we need? Which numbers we need? We needed odd number. Okay. So where are we getting odd number? Here, here, and here. Okay. Now, how is A value when it is an odd number? A is, see here, when it is odd number, your A is 6q plus 1, 6q plus 3 and 6q plus 5. So this is the final conclusion you will write. If A is any odd positive number, then it is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Okay, and hence proved. So is it easy? Very easy, right? So let us see the next question. Using division algorithm, you have to show the square of any positive integer is of this form. Now, when they are saying square, we have to square. This word is important. When they say square, you need to square. Okay. First, let us take Euclid's division algorithm. Okay. And if you compare 3p and 3p plus 1 with a is equal to bq plus r, what is there in the place of b? 3. So, here our b is 3. Okay, and let a be the positive or positive integer. Okay, so let us take case 1. Okay, just have a look here. I think something wrong with the camera. Just give me a minute. Okay. So I hope there was no glitch in the video. I just showed you if a is a positive integer. If you want it as odd number, then there are three cases. I have highlighted here and showed you in yellow color. So odd we got in three cases, second case, fourth case and last case. So when it is odd, how is a? It is a 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5. So that is what we have discussed. So let's proceed to the next question now. Okay. So here they are asking us to prove that a is any positive integer, and now we have to show the square of this positive integer is of the form 3p or 3p plus 1. So I'm comparing it with the Euclid's division lemma a is equal to pq plus r. So when I compare it, my b value is 3 here. Clear? So b is 3. Then r will be between 0 and 3, which means r can be 0 or 1 or less than 3 is 2. So we'll have three basic cases here. So case 1, first, let us write Euclid's division lemma form a equal to bq plus r. So a will be in the place of b we have 3. So 3q plus r, this is equation 1. So case 1 when r is 0. So our equation 1 will become a is equal to 3q plus 0. Okay, or simply I can write as 3p because here it is given in terms of p. I am writing 3p. Okay, see here. One second. Here they asked us the square of the number. So first we need to square. Here comes a very important thing which I said square. They are asking square of the number. So what should we do? When they are asking square of the number, we should square on both the sides. Okay. Suppose if they ask you cube, then you should cube on both the sides. Here they are asking us square, so we will square on both the sides. Okay. So squaring on both the sides, here we have, let's square and see. A square is equal to 3q whole square, or that is equal to 9q square. Or simply we can write as 3 into 3q square. 9 I can write 3 into 3q square. And this 3q square I am taking it as p, so 3 into p. Okay, so square of any positive integer, I wrote it on the form 3p. Clear till here? Now let us take the next one, case 2. So in case 2, r equal to 1. So my first equation will become a is equal to 3q plus 1. And since they are asking square of the number, so we have to square on both the sides. Do you understand now? So squaring a square equal to 3q plus 1 whole square. Or I can write it as a plus b whole square formula. So a square plus b square plus 2 into a into b. So this becomes 9q square plus 1 plus 6q. Or this plus 1 you keep it aside. So 9q square plus 6q plus 1. So from these two again 3 I can take common. So I'll get 3q square plus 2q plus 1. So this I can write it as p because here it is given as p. So 3p plus 1. Okay. Now what is left over with us? Nothing but the third case. So let us see the third case, case number 3. R equal to 2. So our first equation will become a is equal to 3q plus 2, or squaring this we get a square equal to 3q plus 2 the whole square, or simply 9q square plus 2 square is nothing but 4 plus 2ab. So this I can write as 9q square plus 4 plus 2 3s are 6, 6 2s are 12q. Now always remember, I'll tell you one point. First, whatever number you are getting, that you write it in the corner like this. Okay, next, look at this number. This number is greater than the divisor. Our divisor is only 3. But this number 4 is greater than the divisor. So we know that remainder cannot be greater than the divisor. So you cannot write plus 4. So this plus 4 need to be split as 3 plus 1. Okay. Now from this you can take 3 common. So you'll have 3q square plus 6q plus 1 plus 1. Now this entire 3q square plus 6q plus 1 you can take it as p. So you have 3p plus 1. So the square of any positive integer we have proved it is either of the form 3p, or look at the final answers, 3p, 3p plus 1 or 3p plus 1 again. Clear? So this is using Euclid's division algorithm. Now let us go to the next question, next important model. Check whether 6 power n can end with digit 0. So here once let me just revise whatever we have discussed. This is essay question model, children. This is also essay question model. This is short. Okay. So we have covered the most important essay questions from exercise 1.1 now. Okay. Now there is one more short question which is very important. You see. Check whether 6 power n can end with digit 0. Okay. So very simple. 6 power n can be written as 2 into 3 whole power n. Yes or no? 6 can be written as 2 into 3. Now, if I want digit 0 at the end, okay, suppose 10 can be written as 5 twos, or if I have a number 20 can be written as 4 fives, or 4 is nothing but 2 square into 5. So if I want to have 0 at the end, definitely you can see 2 and 5 as a prime factorization. Okay, 2 and 5, both 2 and 5 is in the prime factorization if I want a number 0 at the end. But here if you observe the prime factorization, I have only 2 and 3. 5 is missing. So, our fundamental theorem of arithmetic which we discussed tells you the prime factorization is unique. That means you always the prime numbers are same. Though the order is different, the prime numbers which you get for a particular composite number is always the same. So, there is no scope that you can get 5 into the prime factorization at any point of time. Okay, so 2 and 3 is the only prime factorization. But if I want number 0, I should have 2 and 5. So it is not possible. Okay, getting a number 5 again into this prime factorization is not possible. Because who is telling this? Fundamental theorem of arithmetic is telling you that prime factorization is unique. Okay, so you cannot change it. Therefore, we will conclude that 6 power n cannot end with digit 0. Okay, now whatever steps I told you in words, those 2-3 lines, you will just have to write it here. Okay, that's all. Look at the next question. Now they are asking you, okay, 6 power n doesn't end with digit 0, but will it end with what is the last digit of it? Okay, if not 0, then what is the last digit? So let us understand here. 6 power 1 is 6. 6 squared is 36. So end digit we are concentrating because we want the last digit. 6 cube is 216. So as you observe, all the end digits are 6. So on 6 power 100 also should have some number with a 6 as the last digit. Okay, this is what you will write. Observing the pattern, 6 power 100 will have 6 as the last digit. Clear till now? So these two are the short questions which you can get. Look at the next one. Explain why this is composite number. Okay, we know from fundamental theorem of arithmetic, any composite number can be expressed as product of prime numbers, yes or no, like this. Yes, so here, if I can write it as product of prime numbers, then it is composite. If you just observe here, product, but here I have addition. So I have to remove this. I need to have only multiplication symbol to express it as product. Yes or no? Then I can say it is product of prime numbers. So the given number is composite number. So let's try to write it. So 7 into 11 into 13 plus 13. This is a question given to us. If you observe till here it is one term. This is the next term. In these two 13 is common. So taking 13 common, what is left over here? 7 and 11 plus, right, as it is. Here 13 if I take common, nothing is remaining, so 1. So 13 into 7 11s are 77 plus 1. So 13 into 78. Now 78 I can prime factorize. 2 3s are 6, 2 9s are 3 13s are 13 1s are. So 13 into 78 I can write as 2 into 3 into 13. Okay. Now just observe here. All these are what? Nothing but prime numbers. Okay. And how are they? They are expressed as product. Okay. So all these are prime numbers and they are expressed as product. So product of prime numbers is nothing but composite numbers. Okay. So this is a composite number. This second bit you do it as homework. Clear? Let's proceed to the next question. Find the HCM and LCM using prime factorization method. Very simple. Here you will have only two rules. What is the first rule? Rule number 1. Let me write the rules first. Whenever you want LCM or if you want HCF, what are we going to do? If you want LCM, you will consider all the factors. Okay. Second point, if you have any common factor, if any common factor is there, you will choose the highest power of the common factor. Okay. L means lowest here. L is lowest, so quite opposite, you will choose the highest. What is HCF? For HCF, you will choose only the common factors. First point is only common factor I take. Second point is I choose the lowest power of the common factor. Understand the difference here? Only 2 points you have to understand here. First point is for LCM, we consider all the factors, and if in case if there is any common factor, we will choose the highest power. L means lowest, so you choose the opposite, highest. For HCF, we choose only the common factor. HCF means highest common factor. Okay, the word itself says common factor. So it says I want only common factor. So you will choose only common factor. Second point, you will choose the lowest power of the common factor. So let's understand here. 12, let's prime factors. To 6 are 12, to 3 is a 3 ones. So 12 can be written as 2 into 2 into 3, or simply I can write as 2 square into 3. 15 I can write as 3 fives. So 15 I am writing it as 3 fives. Simply I am just writing it in order. You can write it as you wish. 21. So 3 sevens, 7 ones. So 21 I am writing it as 3 sevens. Okay. So just observe here. We need HCF first. HCF, what is the point for HCF first? First point is common factor. Who is the common factor? 3. Second point, you will choose the highest power of the common factor. Here, 3 power is 1, 1 and 1. So, power is all same. So, no need to choose the lowest power. Sorry. Okay, if there is any power variation, then you choose the lowest power. But as of now, here you don't have to choose any lowest power. Clear? So, next is LCM. So for LCM, what is the rule I told you? All the factors you will consider. So here you have 2 square, 2 as a factor. So you write as it is 2 square with the power you will write. Okay. 3 is a factor, but what is the second rule? When you have the common factor, highest power you will consider. 3 is a common factor only, but there is no highest power. All the powers are 1. So consider it the same. Then 5 is one more factor. You have to consider all the factors. Don't forget. That's it. Simply multiply all this, you will get your final answer. You'll get the LCM if you multiply. Listed. So, rest two, you please do it as a practice question. So, look into the next one. Without performing division, state whether the following rational numbers will have terminating or non-terminating. So, what is the theorem we have learned? If this P by Q, it has terminating decimal expansion if Q is of the form 2 power n 5 power n. Okay, it will have non-terminating decimal expansion if Q is not of the form 2 power n 5 power n. Okay, so we need to concentrate on Q. But before that, one point you just remember, this P by Q has to be lowest form. Okay, you know lowest form of the fraction. Yes, suppose if I have anything which can be cancelled. For example, here I can cancel. 5 3s are 15, 5 4s are 0, 0. So once you get the lowest form, then you will consider the denominator. Clear? So here in 13 by 3125 is already in the lowest form. So I will consider the denominator, which is 3125. So 3125, you will prime factorize and see. 5 6 are 30, 5 2 are 10, 5 5 are 5 1 are 5, then 5 2 are 10, 5 5 are 5 2 are 10, 5 5 are 5 5 are 5 1 are. So I can write as 5 power 1 2 3 4 5. So you might be wondering, there is no 2 here. I did not get any 2 here, so it is non-terminating. No. If you get 5, also it is terminating. If you get 2 alone, also it is terminating. If you get 5 and 2 mixed, also it is terminating. You should not have any other number other than 5 and 2. Did you understand my point? So theorem is this, but remember, simple trick I want to tell you. For terminating decimal expansion, the denominator can have only 5 also, only 2 also, or it can have 2 and 5 together. But other than these two numbers, if you have any other number, suppose if I get 3 here, then directly write it is non-terminating. Okay, so did you understand? If you have 5, if you have 2, or if you have 5 and 2 together, terminating. Any other number other than 5 and 2 is non-terminating. Okay, so why is it so? Because this can be written as 5 power 5 into 1. So 5 power 5 into 1 can be written as 2 power 0, isn't it? So ultimately, if 2 is missing also, I can bring 2 into this. Okay, so if 5 is missing also, you can bring 5 into that. But if you have some other number, then that is completely non-terminating, so you don't have to think about it anymore. Clear? Look at the next one, 11 by 12. So it is already in the simple form. So I cannot cancel it. So I'm taking the denominator 12. 12 can be written as 4 3s. Or 4 is 2 square into 3. So as I told you, if I have any other number here, what is this? Non-terminating. This was terminating. This is non-terminating. Clear now? Is this concept clear to you, everyone? So please do the rest 3 as homework. Look at the next one. Write the following rationals in decimal form. So without dividing, this is without dividing. So how do we do that? So if I want a decimal form, see, suppose if I have 1 by 10, directly I can write 0.1. Suppose 7 by 100, directly I can write as 0.07. Yes or no? So when there is 10, 100, 1000 in the denominator, it is easy for us to write. So our aim will be to write in the form of 10, 100 or 1000. So I have 25 here in the denominator, and I know 25 fours are 100. So I am multiplying and dividing by 4. Is this clear till here? So this gives me 13 fours are 52 by 25 fours are 100. So simply I can write 0.52. Understood? Now 15 by 16. Okay, 16 with what should I multiply so that I can get 100? This is not so direct. So what do we do? So see here, 16 I can write it as 2 power 2 to the 4. 2 to the, so 16 I can write it as, see here, 16 I can write it as 2 power 4. Okay, so to end with digit 0, already I told you, you should have 2 and 5, isn't it? So let us also write 5 power 4. Okay, so we have prime factors to see what is the power of 2. It is 2 power 4. Okay, so now let us write 5 power 4 multiply and divide with 5 power 4. Okay, so what does it give you? 15 into what is 5 power 4? 5 5 is 25, 25 5 is 125, 125 5 is 625. Divided by 16 is nothing but 2 power 4 into 5 power 4 is already there. So 15 into 625 by, this I can write as 2 into 5 whole power 4. So 15 into 625 by 2 into 5 is 10 power 4. Or 15 into 625 by 10 power 4 means 10 with 1 with 4 zeros. Now you can directly multiply the numerator. Whatever answer you get, you can write it happily in the decimal form. Here. So what did I do now? When I was able to directly write, I wrote it directly. If you want this also in the same second method, I will tell you. This was second problem. No? How did we do that? See here. 25, I could simply write 5 square. So 5 square is there. Who is missing? 2 square. 5 is there. Who is missing? 2. 2 with the same power I should take. Here I have 5 square, so here I should take 2 square. So simply I multiply and divide by 2 square. Okay. Here I have 16. 16 was 2 power 4. So 2 is there, 5 is missing. And power has to be same. So 2 power 4 I have. So 5 power 4 I multiplied and divided. Now I hope the concept is clear. Now look at the next most important concept, proof of irrational numbers. So how do we prove irrational numbers? Let us discuss. So the first question is 1 by root 2. You have to prove it as irrational. This is very simple. Whenever you have to prove any number as irrational, first you take it as rational. Okay. So let us assume 1 by root 2 is rational. So if it is rational, it is of the form p by q. Now just reciprocal over. So this side is a irrational number. You know root 2 is irrational and this side is rational number. So irrational cannot be equal to rational. It's a contradiction. So therefore 1 by root 2 is not irrational. Okay, this is the first bit. Okay, now let me do the third bit first. 6 plus root 2. Same model, you will assume it as rational. Then again same thing, you will try to bring irrational number one side and all rational numbers you take it to the other side. Okay, so you know out of 6 and root 2, 6 is rational. So take it to the other side. So you have root 2 equal to p by q minus 6 plus 6 becomes minus 6 and when you take LCM, p minus 6 into q, 6q by q. So again you can see this side root 2 is irrational and this side all this is a rational number. Rational cannot be equal to irrational, so hence our assumption is wrong. Okay, look into the next model, fifth model you see, fifth bit you see, 3 plus 2 root 5. Again you will take it as rational. Okay, and first identify which is the rational term here. 3 is rational, 2 is also rational. So you will try to take all rational numbers one side. So 2 root 5 equal to p by q minus 3. Now you see, let me simplify this, then take 2 to the other side. 2 is also rational. 2 needs to be taken to the other side, isn't it? So 2 is in multiplication, coming this side, transposing, it will become division. So this side is irrational number and this side is a rational number. So rational cannot be equal to irrational. So these are the short answer type questions. Now the remaining which I have left, second and fourth bit are long answer type questions. So let me explain you that. Look at the second bit. You have root 3 plus root 5. All the other three bits which I have done, if you see, there is one rational number, one irrational number in the question given. Did you see? 1 by root 2. 1 is rational, root 2 is irrational. 6 plus root 2. 6 is rational, root 2 is irrational. 3 plus 2 root 5. 3 is rational, root 5 is irrational. You have 2 also in that. Okay, so there is a combination always of rational and irrational in all the three questions which we have done. And whenever there is that such a combination, I did not square. If you just observe, I did not square anywhere. But look into the next model. Root 3 plus root 5. Root 3 is irrational. Root 5 is also irrational. So here comes the problems. What to do? So here, same model. Just assume it as rational. Then take any one number to the other side. So I'm taking root 3 to the other side. After this, you just square. Okay, because both sides you have only irrational numbers, you cannot do anything other than squaring on both the sides. Whereas in previous questions, when you have one rational, one irrational, we did not square. But now, when you have two irrational numbers, you will have to square, remember. So squaring, root 5 whole square is equal to p minus, this I can write as root 3 q by q whole square. So the numerator is from a minus b whole square. So a square plus b square minus 2a into b by q square. Root 5 whole square is 5. Now you can see there is one more step I will write, then you can understand better. Root 3 whole square is 3 q square minus 2 root 3 pq I wrote by q square. You can see very clearly all these are rational, only here you have the irrational number. So our aim is, as you know, rational number one side, irrational number one side. So all rationals one side let us take. So q square, take it to the other side. So 5q square is equal to p square plus 3q square minus 2 root 3 pq. Now these two are also rational, take it to the other side. So you have 5q square minus p square minus 3q square is equal to minus 2 root 3 pq. Okay, so these two q squares I can simplify. 5q square minus 3q square is 2q square minus pq square equal to minus 2 root 3 pq. Now again, root 3 is irrational. These are the rational terms. Isn't it? Take everything to the other side. So everything is in multiplication. Coming to this side, it will go into division. So very clearly, this is irrational number and this is rational number. Again, rational cannot be equal to irrational. We have arrived at a contradiction because our assumption is wrong. Once you learn these lines are same for every question. Okay, the only thing is you have to identify the model. So here I have squared. Why? Because there is no rational number in the question. If there is at least one rational number, you don't have to square, you just have to rearrange it. Okay, let's proceed to the next question. What was the next question? Root 5. Okay, so if you learn root 5, root 2, root 3, root 7, everything is same. First step is same. Let us assume root 5 as rational. Okay, then what do we do? Again, same. You first transpose it. So root 5 into q equal to p. Then you square it first. Squaring on both sides. Same like the previous question. When you square, you have root 5q whole square is equal to p square or 5q square equal to p square. Or let me write p square equal to 5q square is nothing but 5 into q square, isn't it? So I got here that one number is equal to product of two numbers. For example, 6 is equal to 2 into 3. I got p square equal to 5 into q square. It is just like 6 equal to 2 into 3. So when 6 is equal to 2 into 3, can I say 2 divide 6? Can I say that will 2 divide 6? Yes, it will divide, isn't it? So this is also same. Can I say 5 divides p square then? Yes, absolutely. 5 divides p square. We have a theorem. If a square is divided by p, or then a divides, sorry, I wrote the reverse of it. If p divides a square, then p divides a. Isn't it? We discussed this theorem. So 5 divides p square. So 5 also divides p. Okay? Keep it in a box. If 5 is dividing p, see, I said 2 is dividing 6. So I can write 6 equal to 2 into some number. So if 5 is dividing p, I can write this p is equal to 5 into some number. Let that some number be c. Okay? This 5c, you keep it in this equation, previous equation. Okay, so you have 5c whole square is equal to 5 into q square. Or 5 square is 25, c square equal to 5q square. Take this 5 to the other side. So you have 25 c square by 5 equal to q square. 5 ones are 5 5s are 5 c square equal to q square. Again, see, same steps. These two are same. See, q square equal to 5 into c square. It is like that. So I can say 5 divides. All the steps are repeating. 5 divides q square. Then if 5 divides q square, 5 also divides q. You just observe all the steps are repeating. Right? 5 is dividing q, which means what? 5 is a common factor of p and q. 5 can divide p it seems and 5 can also divide q it seems. Okay, so see here. For example, 2 can divide 6. This is possible. And 2 can divide 12 also. This is also possible. That means 2 is what? Common factor for 6 and 12. Isn't it? But when it is a rational number, here p and q are co-prime. What does co-prime mean? Co-prime means no common factor. One is common factor of every number, but other than 1, there should be no common factor. But here you got 5 as a common factor, which is a contradiction. And why did we arrive at this contradiction? Because our assumption is wrong. Okay? So therefore, you conclude that root 5 is irrational. Clear? So let's proceed to the next. Yes. Let's enter into logarithms now. When you have to find the value of a logarithm, which is like this, first of all, see, you have a big number. Whenever you have a big number like that, okay, you prime factorize it. So 2 8s are 16, 4s are 2s are 2 1s are. So log 16, I can write 2 power 4 to the base 2 minus log 2 to the base 2. This is like log x power m. So I told you this just jumps in front of the logarithm. So m log x minus log 2 to the base 2 is 1. So 4 log 2 to the base 2 is 1 minus 1. So 4 minus 1, that is 3. Done. Okay? Clear everyone? Okay? So here when you are writing this, you have to mention all the formulas whatever you are using. That is very important. M log x. You should please write the formulas. Look at this question. Log root x, I can write x power 1 by 2. Now simple, just power jumps front. And half log x to the base x is 1. That's it. Now here you see, first I have to simplify it as single logarithm. So let me take 2 together. So before taking that, here this is not simplified. Let me take it in simplified form. We know log x power m is m log x. Log x power m is this m jumps front, m log x. The reverse is also true. This is like the reverse. M log x is log x power m. So this 2 should go to the power. So it will become log 3 square. Minus log 2, right as it is. Okay, now these two let us combine. So log, we know log A plus log B is equal to log A into B. So log 10 into 3 square is 9 minus log 2. So log 90 minus log 2. Log 90 minus log 2 is log 90 by 2. Yes or no? So we have log A minus log B is equal to log A B. So you have log 45. 90 by 2 is 45. Clear? See the next one. Log 60 you have to express as x and y. Okay. First of all, I said whenever big number is there, first you prime factorize. So 3 tens are 5 twos. So 60 I can write it as 2 into 3 into 5 into 1 more 2. So I'm writing it as 2 square. This is like log A into B. So you can divide it log A plus log B plus log C. Now here power is there. So power goes front. So 2 log 2 plus log 3 plus log 5. Again here log 2 to the base 2. Same log. So it becomes 1 plus log 3 plus log 5. Log 3 to the base 2 is x. So 2 into 1 is 2. Log 3 to the base is given as x plus log 5 to the base 2 is given as y. So this is a simple answer you get. Okay. The only one funda is learn all the formula of logarithm first. Then whenever you find a big number, first prime factorize that particular number. Clear? So next, log 1000. 1000 is again big number. If you prime factorize, you'll get 10 cube. So it is nothing but 3 log 10. That's it. A log 10 again, if you want to expand, you can expand. Otherwise, here log 10 to the base 10 will be usually, okay. So if nothing is written as a base for class 10, it is 10 as a base, okay. So log 10 to the base 10 is 1, as you know already. So you have it as 3 into 1, which is nothing but 3. Okay, look at this question. This you can write as log x cube by y square whole power 1 by 2. Whenever root is there, it is power 1 by 2. So log x cube power 1 by 2 by y square power 1 by 2. This I can separate. It is like log a by b. So log a minus log b. Here 2 cancel, so you will get only y. Okay. So it is nothing but log x power 3 by 2. I can write here minus log y. Done. Here. Look into the next model. It is given x square plus y square is 25xy. You have to prove this. First of all, look at the LHS of what you have to prove. This is nothing but m log x. So I can write log x power m formula. This 2 goes into the power. Okay, so again what is this? This is x square plus y square plus 2xy. So if you just observe, x square plus y square is there in what is given to you. Given x square plus y square equal to 25xy. So x square plus y square is there. What is missing? 2xy. So that 2xy you add on both the sides. Understood? Once you analyze your LHS, then you know that 2xy I should add. Now this is nothing but x plus y whole square formula. This is nothing but 27xy. Now apply logarithm. What else is missing here? Logarithm. Apply logarithm. So log on both the sides I apply. Now this is by like log x power m. So m comes front. So m log x is equal to, this is like log a into log b. So log a plus log b plus log c. Again, whenever big number is there, I said you have to simplify. 27 I can write as 3 cube. 3 into 3 into 3. Log x plus log y. Now again one more formula you can apply. 3 goes front. Log x power m formula. And here comes your proof. Such a simple proof it is, but children break the head because they don't understand the logic, why we are adding anything. Why did we add? Clue is in the question only. So just check what you have to prove. In what you have to prove, just do the reverse engineering. Okay. So you will know that I want x plus y whole square. In x plus y whole square, 2xy is missing. So that 2xy you add. Enough. Then apply logarithm and there ends the matter. Clear? Let's see the next question. So here you see we have to find the value of this. Okay. And you said, ma'am, you said in the previous question, whatever I have to prove, I'll get the answer. But here nothing is there. Okay. So you just take what is given to you. Equal to half log xy. Half log. Log xy is nothing but log x plus log y is log x into 1. Now this half can go to the power. So you have log xy to the power half. What is that power half means? Root xy, isn't it? So I have two sides single logarithm. So I can cancel the logarithm and I can just take the inside values as equal. Okay. Now please square on both the sides because you have a root. We need to remove the root. So you have x plus y whole square by 3 square is equal to root xy whole square. So this is a plus b whole square formula. A square plus b square plus 2ab. 3 square is 9 is equal to root xy whole square is xy. Now this 9 you take it to the other side. So you have x square plus y square plus 2xy is equal to 9xy. Now 2xy you take it to the other side. So x square plus y square equal to 9xy minus 2xy. So 9 minus 2 is 7xy. Okay. Now xy you take this side because we want something like x by y, y by x. So something should be in the denominator. So let me take xy to the denominator. So x square by xy plus y square by xy equal to 7. So x and x cancel, y and y cancel. So x by y plus y by x equal to 7. Got it? So just by looking at the question, you cannot tell that it is a difficult question unless you do it. Okay, once you start doing it, just apply the formulas what you know. You don't have to do anything magical here. What you have to do, you know the formula. You know that there is log x plus log y, which I can write as log x y. Then that half is there, that half can go to the power. Now both sides single logarithm is there, so you just cancel it and just equate it. Square is there, square root is there, so to remove that I have to square. Simple things. Once you do the step, you will automatically understand what should be the next step. Okay. So this, please do it as a homework. Okay, try and tell me if you're able to do it or not. That is an important question. So let's proceed to the next chapter, sets. So within 1 hour, I hope I have given you a clear idea of real numbers. Now it's your part to practice it once. Okay. So this is again a very important chapter. Definitely you will get heavy weightage from this chapter. Okay. Minimum of 8 marks. Most important questions we are going to discuss now. Okay. First, let us talk about the concept. We have only limited concepts in this chapter. First is roster form and set builder form. You need to understand this. Okay. Roster form is, suppose A is a set containing elements 1, 2, 3, 4. This is called roster form. Simply, if I ask you what are the elements of A, immediately you can take out and say, ma'am, in set A has 1, 2, 3, 4. Set builder is nothing but you have to build the set. You are the builder now, you have to build the set. So, suppose it is denoted like this. A is a set containing element X such that X is a natural number, it belongs to natural number, and this X is less than 5. What does it mean? X belongs to natural numbers means it has to start from 1 and is less than 5. So, starting point and ending point is defined. Okay, so if I want to write the roster form, see, this is the roster form. 1, 2, 3, 4 is the roster form and set builder form. Is it clear now? What is roster, what is set builder is clear to you? Fine. Okay, so next is finite and infinite. If the number of elements in a set are limited, it is called finite. For example, just now we saw A equal to 1, 2, 3, 4. Only till 4 if I take, this is finite. Infinite, if I take A equal to all the natural numbers. So starts from 1 and it just continues. So it is infinite set. Okay. In set builder form, how do you write it? A equal to A contains elements X such that X belongs to natural number. That's it. What is only lower limit is given. What is the X upper limit? It is not given. So it is infinite set. Clear. Then we have null set. Null set is nothing but an empty set. It doesn't have any element. Okay. Then we have a concept called subset. Subset. What does it mean? Suppose if I have a set A, I'm again taking the same example. Subset means part of the set. Okay. So 1, if I take 1, single element 1, single element 2, single element 3, single element 4. Or if I take 2 elements together, 1, 2, then 1, 3, then 1 with 4. Okay, so I took single element, then 1 with 2, 1 with 3, 1 with 4. Then I can take 2 with 3, then I can take 2 with 4, then I can take 2 with 3 with 4. Okay, 2, 3, 3, 2 is already over. And remember one more very important thing. Elements of a set cannot repeat. You cannot repeat the elements. Okay, and if I write 2, 3, that is equal to 3, 2. So order, if I change also, no problem. It represents the same set. Okay, so you don't have to write again. And then the total set 1, 2, 3, 3 elements I'm taking. Then 1, 2, 4. Then let us take 1, 3, 4. Okay, then you can take 2, 3, 4. Then you can take the full set 1, 2, 3, 4. Every set is a subset of itself. Okay, so the same set you can take, and null set is subset of every set. Empty set is this is called null set or empty set. This is a subset of every set. So totally how many subsets you will get? 2 power 4. Okay, how many elements are there? 4. So 2 power 4. That 4 is called cardinal number. How many elements are there? The number of elements in the set, if you count and tell, that is called cardinal number. And you can count the elements in only finite sets, isn't it? You cannot count the elements in infinite sets, right? So this is the concept. Then we have, these are the basic things which you have to know. Then we have something called union intersection. Okay, let's do it. Along with Venn diagram, in one question I'll teach you. So suppose A is a set containing elements X such that X belongs to natural number and X is less than 9, for example. B is a set containing elements X such that X belongs to whole number and X is less than 5. C is a set containing elements X such that X belongs to natural number and is of the form 2n plus 1, where n is a what shall we say, n, let me give a condition for n. N is natural number and n is less than 5, for example. Okay, now they're asking you to find A union B. A union B union C, A intersection B, and B intersection C. For example, these things. Okay. They may ask you like this also, N of A union B union C. N of means cardinal number they are asking. Okay. So, have a look here. First of all, to conduct any operation, union or intersection or difference also let us cover in the same question. A minus B, B minus C, C minus A, something like that. Now, whenever you have any operations to do on the sets, first you have to convert them to roster form. Unless you know what are the elements, you don't know how to do the operation. So, first, A. Okay, all these are set builders form. You see, elements are not directly listed. You have to list them. So, let me convert to roster form. Okay, so x belongs to natural number. That means they start from 1. And x is less than 9. That means I should stop at 8. So, 1, 2, 3, 4, 5, 6, 7, 8. Now B, x belongs to whole numbers, that means they start from 0, and x is less than 5, that means I have to stop at 4. C, x is natural number, okay, and x is equal to 2n plus 1. What is given to us? X is 2n plus 1. And first to find x, I should substitute something in the place of n. How is n? N is natural number, that means n starts from 1, and n is less than 5, that means n is from 1 to 4. Okay, so suppose if I take n equal to 1, then x will be 2 into 1 plus 1. So x will be 3. If I take n equal to 2, x will be 2 into 2 plus 1, that is 5. If I take n as 3, then x is 2 into 3 plus 1, which is 7. If I take n as 4, then x is 2 into 4 plus 1, which is 9. So I have the values of x. You should not write the values of n here. This is x set. Okay, so x values I should write 3, 5, 7, 9. Okay, now if I have to find the first bit A union B. So you'll write the elements of A and B. Okay, A is 1, 2, 3, 4, 5, 6, 7, 8. Union B is 0, 1, 2, 3, 4. Union means all together. Okay, but one point you remember, I told you elements of a set are not repeated. So when you're writing it together, please don't repeat it. So I have 1, 2, 3, 4, 5, 6, 7, 8. These are the elements of A. First write all of them. Then B you see. In B I have 0. 0 I can actually write first. Okay. Then 1, 2, 3, 4 already we wrote, so we don't have to write. So this is A union B. If you have to represent it as Venn diagram, how do you do? First, you draw a rectangle. This represents the universal set. Then you have set A, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you have set B. If you clearly observe, set B has, okay, 1 second. Set B is not the entire numbers here. There is little common, little uncommon elements. So let us understand both. Only few are common. Okay, so see here. What is not common? Let us write that. First, what is common? Let us write 1, 2, 3, 4. 1, 2, 3, 4 is common. So what is common? You write here in the common section. After 1, 2, 3, 4, what is remaining in set A? 5, 6, 7, 8. That you write anywhere you wish inside A. Then in B, what is left over? 0. Now when I say union, you see you actually got all this. This is nothing but A union B. Clear? Suppose if I want A intersection B. So A is 1, 2, 3, 4, 5, 6, 7, 8. Intersection means only the common things we write. Intersection. B is 0, 1, 2, 3, 4. So what is common here? 1, 2, 3, 4. So if I have to represent as Venn diagram, set A, set B, what is common? 1, 2, 3, 4. 5, 6, 7, 8 is here and 0 is the not common element of B. So whatever is common is only the middle portion. This is A intersection B. Suppose if I want A minus B. So A is 1, 2, 3, 4, 5, 6, 7, 8. Minus B is 0, 1, 2, 3, 4. A minus B means from A I should remove B. Okay, please understand this concept. So from this A, I should remove B. That means the common elements of B I should remove. What is common? 1, 2, 3, 4. So these I should remove from A. What is remaining is nothing but A minus B. Did you understand? So if I have to draw the Venn diagram, A, B, 1, 2, 3, 4, 5, 6, 7, 8 and 0. If I have to remove the common area of A and B, so this is A minus B. Then how do you get B minus A? Any idea? B is 0, 1, 2, 3, 4. A is 1, 2, 3, 4, 5, 6, 7, 8. Okay. So from B, I should remove A. Okay. So that means the common elements I should remove. So in from A and B common are 1, 2, 3, 4. So this I should remove from B. What is remaining? Only 0. So this is B minus A. So where is that portion? This is B minus A and this side is A minus B. Clear, children? So when they ask you to draw the Venn diagram, you can draw it separately, but just for your understanding, I told you like this. Now if they ask you n of B minus A, that means how many elements are there in B minus A? First you will find B minus A. I found B minus A, I got 0. So how many elements are there? One element is there. See, 0 is there. Okay, there is a difference between null set. Null set has nothing inside it. But if you have 0, many students get confused. This is not null set. This is null set. Here 0 elements are there. How many elements are there? If I ask you how many elements are there in null set, you say 0. But how many elements are there in this set? Number of elements, suppose if this is set A, how many elements are there in A? If I ask you, it is 1. Clear? So with this, I have completed all the concepts. You just finished B minus C, C minus A. With the C, you try to do the operations. Okay. So I have completed all these problems already. I have done. So all this is done, children. The first two chapters, I only want you to practice. Okay. Second chapter, don't focus much on it. I mean, it has a heavy weightage, but you don't have to worry regarding the number of problems. If you're able to do perfectly whatever I told you, these concepts, converting to roster form and then finding the operations A minus B, B minus A and all and N of, then your job is done. You're all perfect with it. So in a very limited time, I try to cover everything which is needed for your exam, and I hope this video is super helpful for you. So please do subscribe. Please comment and let me know your feedback. Otherwise, I feel the students are not listening, and then I doubt whether I have to continue the classes or not. So please subscribe, please comment, like the video so that it reaches many students, and do share it in your class group. Bye bye. Take care. I will come with a new chapter again.